In the name of Almighty God, I'm Mahsa Sankashi, and today I want to talk about heat transfer for single-phase liquid fluid in micropin configuration of microchannel. Recent technological advancements have led to a drastic increase in heat flux dissipation, which is a prime factor for lower efficiency and permanent failure. Therefore, cooling methods require consistent upgradation to cope with the demand. Among various innovative techniques, the microchannel heatsink has gained much attention. Furthermore, the micropin configuration of the microchannel has yielded better performance than the conventional microchannel due to greater convective area, secondary fluid flow, unique vortex production, and also thinner boundary layers. The present review simulation systematically analyzes different aspects of micropin fin. For example, its cross-sectional shape, arrangement density, and also design parameters. The design parameters including aspect ratio, side wall gap, tip clearance, and etc. We truly described and their optimal range were elaborated. It was observed that vortex formation downstream of the pin fin significantly influences thermohydraulic performance and can be analyzed with the help of a streamlined plot of fluid flow. Based on different studies, it was concluded that the optimal micropin heat sink for single-phase fluid flow should have been fin with sharp edge cross-section, pin porosity in range of zero point 0.5 to zero point 0.6, tip clearance of 15 to 25% of channel height, staggered fashion, and stepped arrangement. Furthermore, there is a considerable scope for innovative pin fins as pin fins like open rings and lattice structure have shown effective cooling compared to conventional pin fins. With recent advancement in various technologies, the heat flux has been increasingly drastically over time, and it may exceed 1000 watt per square centimeter in the near future. If such a high amount of heat is not evacuated from the system, it may impair system performance. Further, it can also lead to permanent failure. The effective thermal management is one of the main reasons for losing over 50% of all of electronic circuits. Another critical factor for increased heat dissipation is because of significant shifts towards renewable energy drives. Furthermore, emerging domains like battery thermal management system, hydrogen generation, and storage also had the central issue of high heat flux dissipation. Earlier forced or natural air cooling using conventional pin fins is enough as heat flux dissipation was very low. However, with the increase in heat generation, these devices cannot fulfill the demand. In addition to it, these devices are bulky and loud, so researchers started focusing on liquid working fluid, as the liquid has higher thermal conductivity than air and comparatively offers up to 10 times increase in heat transfer rate. To address the issue of high heat flux dissipation, several strategies, including spray cooling, microheat pipes, jet impingement, and etc., have recently been developed. Based these techniques, fluid flow through a microchannel heatsink has gained worldwide attention due to favorable characteristics such as high surface to volume ratio, lesser material cost, low coolant requirement, quick response time, and etc. The fluid flow characteristics in microchannel significantly differ from the conventional channels as shear and surface tension forces become more significant and the influence of gravity forces reduces. Channels having the size in order of micromillimeter or micro or millimeter are recognized as microchannels. Despite this, researchers confidently identify and acknowledge the channels as microchannels if their diameter fall within 100 to 1000 micrometer, according to the currently available literature. Due to simple construction, microchannel heatsinks offers vast applications in electronic cooling, reactor blankets, rocket engine and refrigerator cooling, and also hydrogen storage. Despite various merits, Microheat sinks Microchannel heat sinks has limitations regarding increased pressure drop, leak-proof arrangement, entrapment of foreign particle, scaling, and etc. Since the inception of microchannel by Tuckerman and Pease in electronic cooling, significant research has been conducted to understand fluid flow mechanics and heat transmission through microchannels. Efforts have also been made to improve the overall performance of the thermal hydraulic system. Generally, two different techniques have been opted to enhance the performance. The first one is external and the second one is internal methods. As illustrated in concept simulation, in external methods, external power sources are used to influence the fluid flow characteristics in the microchannel. Approaches like flow pulsation, electrostatic fields, and magnetohydrodynamics and vibration fall under this category and have been studied to see the influence on heat transfer performance. While in internal techniques, the second one modifications are done either in microchannel design or working fluid. There is no requirement for any external factor in this method due to that it's more widespread. Recommendation for future works. Numerous attempts have been made to improve the thermohydraulic performance of MPFHS due to the rapidly rising heat flux production in various sophisticated devices, so that proper thermal management can prevail. MPFHS has shown tremendous potential. Much research will further augment such devices' capability. Therefore, based on the present review, some techniques that can be further explored or investigated to were listed below. The first one is to improve heat transmission vortex generations like protrusions, dimples, and etc. can be used in micropin fins. Furthermore, very little experimental work has been reported in the literature and can be performed. The second one is MPFHS can be used in various innovation combinations like waveness and double layer. The third one is thermal and hydraulic performance of MPFHS strongly depends upon surface parameters like channel walls roughness, hydrophobic and also hydrophilic, and also coated surfaces can be investigated. The fourth one is Proust type micropin fins has been rarely explored and can be investigated to augment the thermal performance. The fifth one is different nanofluids PCM slurries can be implemented with MPFHS to enhance thermal performance further. Different nanoparticle (PCM) particles can base fluids can be applied in a heat sink. The sixth one is few researchers have worked on two-phase fluid flow through MPFHS. These geometrics can also help mitigate the instabilities like flow reversal, bubble clogging, pressure and temperature fluctuations. The seventh one, the use of external techniques for secondary fluid flow and pressure-driven main flow in MPFHS has vast scope in its application. The micro-pinfin arrangement of the micro-channel heatsink has been truly researched in the current review simulation. Compared to microchannel heatsinks, which favor improved thermal performance, micropifin heatsinks have several intrinsic benefits like higher convective area, secondary fluid flow, vortex production, and thinner boundary layer. Different design approaches have been made in micropifin heatsinks to enhance heat transfer due to the fast rise in heat flux in various electronics. The design alteration in the micropin fin heatsink can positively or negatively influence flow characteristics. Two important parameters are always kept while designing any new micropin heatsink. Firstly, the fluid flow should be uniformly distributed throughout the heatsink. Secondly, there should be no local hotspot generation in the bottom wall of the heatsink. Uniform substrate temperature, and moreover, based on the present work, it was observed that the following points should be considered while designing an effective micropin fin heatsink. The first one is micropin fin have sharp pointed shapes, has better heat transfer capabilities than compared to a streamlined shape. Further, various innovative pin fin cross sections, like open ring, perform comparatively better than traditional cross sections. The second one is that optimal range of porosity for micropin fin is zero point 0.5 to zero point 0.6 for enhanced performance. The third one is the staggered arrangement has consistently shown better thermal performance than the inline arrangement, but at the expense of pressure drop. The fourth one is for augmented performance. The sidewall gap to pin-fin diameter ratio should kept between zero point 0.8 to 1.1. The fifth one is the tip clearance in the heatsink should be a manageable size. The optimal range for the tip clearance is 15 to 20% of the channel height. The sixth conclusion is a pin-fin height variation along the channel length must be arranged in an increasing pattern, as the decreasing pattern has shown inferior performance compared with the growing design. And the last but not least, better flow mixing has resulted from the stepped arrangement of pin-fin along the length and the breadth of the channel than from the step arrangement along the channel length alone. And as you see here in my simulation in the console software, you can see that I have used two different physics heat transfer in solid and fluids, and the next one is laminar flow to study about the pressure, velocity, and also temperature in fluid. You can download the full of this simulation from my GitHub as a master script, and the name is Console Heat Transfer Analysis for Microchannel and Micropins. Thank you so much for watching until then.